I would say first, I also want to take a minute to introduce myself. I am, as already introduced, Alexander Smalka. I am from Germany. I'm a researcher at the Technical University of Munich and working at the Lunar and Planetary Exploration Professorship. I am working mainly on the modeling of the lunar exosphere. And while previously, when I started working on this topic, when I started at the internship at JPL, I was really just looking at general mechanics of the exosphere, focusing mostly on noble gases. We're going to cover that later on because they're just a little bit easier to handle. And now I migrated towards hydrogen-based gases, focusing a lot on the water exosphere, which is inherently a little bit more interesting and a little bit more complicated because its interaction with the surface is so much different. My methodology is basically just numerical modeling. So I'm a numerical scientist, and I'm really much excited to be here because this is really my opportunity to learn a little bit more about experimental science and hopefully be able to combine these two things. I am not a physicist by trade. I'm coming from an engineering background. So I studied mechanical engineering in Germany at the RWTH Aachen University, and then moved on to Munich for my master's degree in aerospace, where I then got to be a little bit closer to physics, really trying to be a bridge towards science, or trying to be somewhere between engineering and science. And this is also really what we're trying to go for at my home university. And I just also want to quickly introduce that. While there was previously only the central campus in Munich and the technology campus in Garching in the very north, we just got like two more major additions, one in the very west of Munich in Oberpfaffenhofen, and one which is my campus, or the campus where I'm working at, which is the Ottobrunn campus in southeastern Munich. And you can see this is very much just an advertisement slide I copied plainly from the university side, where they depict all the nice cooperations the university is going for. Nonetheless, it's very nice to be out there and actually do some cooperations with startups, with other aerospace industry, which is always also nice for students, motivates them to come down, motivates them to work there, and to work in the aerospace industry. I'm working for Professor Philipp Reis at the, as I said, Lunar and Planetary Exploration Professorship. And usually what I try to say when I describe what we're working on is really to be somewhere between the technical side, the engineering side of the university, and being the bridge to the science side. So we're not really just engineering. We're definitely not pure science. We try to be somewhere in between. On the one hand, and also, again, I copied that plainly from our website, what the three biggest topics are that we're working on. We're trying to better understand what is out there in our solar system. So the main focus of Professor Reis is space resources, looking at how can we find them, how can we quantify them, and then on the technology side of view, how can we extract them, how can we utilize them. So really trying to answer what is out there, how did it get there, and how much is out there in our solar system. My own focus is then again on the moon, and mostly focusing on the water content that we can find on the moon and how did it get there. But as I said, we're also looking at the engineering side, trying to work on instrumentation to better characterize it, find it, and measure its abundance, so to speak, but also technologies concerning the extraction and utilization of resources. So just a rough idea of the background and why I'm standing here today. And with this, I think we can start with the actual topic, which is the lunar exosphere. And I'm really trying to not bore you, but I wanted to establish a couple of ground facts and a couple of main ideas that my research is really focused on. So I'm working on the lunar exosphere. Most of the things that I'm going to talk about apply to other exospheres that we find in our solar system. But there's one specific difference that compared to, for example, Earth's exosphere. Here on Earth, the exosphere is just, so to speak, another layer on the atmosphere that we already have. A very high up layer where it's getting very, very thin, essentially so thin that particles are moving freely without ever interacting with each other. for the moon, and we have similar conditions, for example, on Mercury, we have similar conditions on some of the Saturn moons, Rhea, I think Europa. Some of the modelers are looking at asteroids, so Ceres. So all of these are so-called surface-bounded exospheres, meaning that the exobase, the really base of this exospheric layer, is already the surface of the planetary body. So I just, again, copied one of the explanations, one of the definitions, such as surface-bounded exosphere is an atmosphere-like volume surrounding a planet or planetary body, so to speak, where molecules are gravitationally bound to that body, but where the density is so low that the molecules are essentially collisionless. And this last point, essentially collisionless, is the main advantage that we have when it's about the modeling process, because essentially collisionless means that we can take each individual particle, and I just, for clarification, added 5 of them in this sketch. After that, I got bored with PowerPoint and trying to sketch in particles, but you can see them and see each individual particle's trajectory. And because it's collisionless, because they are not interacting with each other, once you know the starting position, once you know the starting velocity of a particle, you can basically just track it through its course through the exosphere, and then use all of these trajectories to calculate densities, calculate abundances at different spaces. So that is just a very nice thing from a modeling perspective. We can all model them individually. There's still one problem. Yuri already touched on this. It is much, much thinner than the atmosphere that we have here on Earth, but there's still not nothing in the lunar exosphere. I just copied the first couple of numbers that I found in my documentation, starting at hydrogen, going to neon, and you see there are varying abundances in the lunar exosphere, and it really much depends on the day side, the night side, whether you're close to the equator, whether you're closer to the poles. But there is still a substantial amount of particles in the lunar exosphere. You have mostly noble gases, helium, neon, and I omitted it, but argon is also a very frequent or a very high abundance in the exosphere, which amounts to somewhere between 10 to the 5, 10 to the 4, 10 to the 5, maybe a little bit more particles per cubic centimeter. Again, that sounds much, but if you compare it to Earth's atmosphere, where we have about 2 times 10 to the 19 particles per cubic centimeter, you see it's still a very nice vacuum. There's still not that much going on. Nonetheless, way too many to say we simulate each of them individually. We can simulate some of them, but just out of computational effort speaking, we cannot simulate all of them. But this is a very usual problem that many people see, that many people face. Simulation that we can do individually, but not for all of them. We have to do some statistics, and the usual approach, the usual method you use, which is a very popular method for exospheric modeling, is to use a Monte Carlo simulation, is to use a Monte Carlo method, and then repeat the modeling process of individual particles often enough until you get an idea of the statistical ensemble of particles in the lunar exosphere. And really what you have to do now that you already established you want to use a Monte Carlo simulation, trajectories are basically just solving the ODE for gravitationally bound particles in the exosphere. You have to see, okay, what are my drivers? What is happening to my particles on the moon in the exosphere? But also, where do they originate from? What are my sources? And where do they end up? Where are my sinks? And here again, it varies from species to species, but main sources that you can see in the lunar exosphere are the solar wind. So any kind of particles coming directly from the sun. There you have, I think it's on the next slide, you have mostly protons and electrons. I think the rest of the ions are mostly helium or alpha particles. And then there's a subset of much, much fewer particles. You have some carbon ions, some oxygen ions, but compared to the abundance of protons, there's really not that much going on. On another hand, you have micrometeoroids that on the one side bring material because they are made out of something to the moon, but through their impact, through the energy transport that they provide to the surface impact, so to speak, they vaporize everything that they have, or some of the regolith and some of their own material. And this vaporization will just then fuel again the exosphere for the components that the regolith and that the meteoroid is made of. So in my case, if you look at meteoroids, say that they're mostly made out of water, meteoroid impact vaporization would say that we have a localized source of water for the exosphere. You also have sputtering. So in case you really want to focus on species that are coming from the lunar surface itself, you have solar particles hitting the lunar surface that are just then sputter out some of the particles that you can find in regolith grains. So these are just some of the sources. I think on later slides, you will see other endogenic sources, something like where argon is coming from, radioactive decay of potassium, which is already in the crust of the lunar surface. So you have other kinds of sources, but usually this is what I'm focusing on. And because I'm mostly looking at the water exosphere, mostly looking at hydrogen-based gases, my main focus is the solar wind and micrometeoroids. On the sink side, we kind of can combine one half of all of these things to gravitational escape. Basically, any kind of process that is accelerating our particles above escape velocity, meaning that they will just escape the lunar exosphere for good. So this could be either just thermal release, if they are inherently hot enough, if they thermally accommodate to the ground, getting enough thermal energy to then reach escape velocity, which is especially relevant for the light species, obviously, for hydrogen, helium, but it levels off quite quickly. And for the moon, you have the distinction very, very close to water, so very close to atomic mass unit of 18, where not that much of loss is happening anymore, just based on thermal desorption. You have other processes. Again, sputtering is one of them, which is involved with a lot of energy, providing a lot of energy to the particles. You have photodissociation, photoionization going on, especially obviously on the sun side of the moon. So enough physical processes that can accelerate the particles and let them leave the exosphere. But there's a second sink that you can see, which is not through the exosphere, which is then what Yuli already touched on the surface of the moon itself. If you have some places on the moon which are cold enough to permanently freeze particles that will hit these cold spaces, and if these places essentially will never reach enough sunlight to ever heat up to a specific temperature, particles can get trapped in there in these permanently shadowed regions and then remain permanently trapped on the lunar surface. So these are also some of the things that you have to consider. Yeah, I already took that away. So my main point is I'm looking mainly at the solar wind, and there I'm mainly looking at protons simply because these are the most abundant species of solar wind particles, solar wind ions that are hitting the lunar surface. And with this, I already want to show you basically my first simulation. So back when I was at JPL, I started my first lunar exosphere simulation, and there I wasn't yet concerned with hydrogen. I just wanted to make everything work, see if I can input all of the sinks, all of the sources, can get most of the mechanisms right without having to worry too much about what's happening on the ground. So I set up my Monte Carlo simulation. I wrote all the code myself, which is a completely custom model, so I can really have full control over what's going on. But for simplicity reasons, I didn't have too much time. I focused mainly on noble gases, so helium, neon, argon. Shortly looked at heavier noble gases as well, but these three were my main cases where I tried to make that model work in the first place. And I found this graphic. I think it's back from my master thesis as well. So I'm very glad that I can find it again, where I tried to combine all of the effects that went into my old model. So you have different kinds of sources, which can be the sun here on the side, providing ions. Ions will pick up electrons on the first impact, basically on the lunar surface, and then fueling the neutral atmosphere of some element. I called it A in this sketch. Then you can have a different kind of source, which is then endogenic, where you have some radioactive material. I already said argon is a very prominent example here. You have already potassium in the lunar crust, and over time it will radioactively decay to argon, form like bubbles of argon that are submerged in the lunar ground. And once you have some moonquakes, any kind of movement going on, you can actually have some argon diffusing out to the lunar surface and then fueling the argon exosphere. So these are the main inputs that you can have. Here, back then, I didn't look at micrometeoroids. These were my only two inputs that I have. And then you have obviously a couple of outputs. On the top, you have just gravitational escape. So anytime the velocity is bigger than the escape velocity, they're basically gone. But you also have the interaction with the sun, with sunlight. So you have any kind of photolysis going on, photoionization that would ionize the exosphere, at which point my code had troubles working with it because it was really just focusing on gravitational forces. But there are a couple of nice papers who already investigated how ions behave in the exosphere, saying that some of them will probably eventually intersect with the surface where they undergo the same cycle of picking up another electron and be recycled. So there was this recycling factor going on, which can be in the order of 1/2 down to 1/10 for different species. And so even though the ion exosphere wasn't modeled yet, I just included this recycle factor, say, okay, of all that are lost due to ionization, some of them will just be recycled and will replenish the neutral exosphere. Lastly, I also included this cold trapping, where I just said, okay, if it's cold enough, if it's will be absorbed, if the residence time is much, much, much longer than a lunar day, and over the course of a lunar day, there's no time at which the temperature rises to a point where this would change drastically or in any way meaningful, I said, okay, they're lost permanently. They're now stuck to the ground and not part of the exosphere anymore. I put some of the assumptions there. That's very good. So some of the assumptions back then was, because I was only using gravitational forces, I was able to speed up the process by just analytically calculating the landing positions. I didn't need to implement a good ODE solver here to really track my particle over the entire trajectory. For just gravitational problems, you were able to calculate the landing positions and then use the landing positions to look at surface densities. And this was the main reason why I was really not able to look at ions. I had to go for only neutral gases to make that work. But it was enough. I calculated my exosphere for a couple of different species and then compared them to whatever I can find. And even though for the moon, the data is somewhat available, the most reliable data that I can find, at least for the comparison, was really just out of other papers that I can find. So data is always a thing. And for other modelers that are looking at Ceres, at Mercury, it's getting more and more difficult because less and less and less data is available. But here I compared my model to 3 others where I just plotted my results over there. So what you can see is a global distribution of surface densities where the top side of the figure is always the exact copy out of the paper, and the bottom side of each figure is my own solution from my model that I had back then. And I don't want to go into too much detail. I will show you some more of these graphs later on. It's just to see that it's quite close. It's quite close, where I would say, okay, the basic dynamics of the global exosphere behavior for certain species is matched for their model and my model. And that was, at this point, very, very good. At least for my master thesis, it was quite nice. Nonetheless, there is a distinct difference between different species. For the first graph that I now zoomed in, we see helium. And here, I just want to point out a couple of things. You see, the x-axis is given in local time. So really the solar time that you currently have on the moon, 6 o'clock, meaning it's sunrise on the moon, 12 o'clock, meaning it's the subsolar time. It's really noon right now. And at 18 o'clock, the sun sets again. So everything between 6 and 18 is daytime, and everything between 18 o'clock and 6 o'clock will be nighttime. And for helium, you see, there's a huge gap on the day side, which was to be expected. On the day side, you have very, very high temperatures going up to about 400 Kelvin, which is way more than enough for helium to basically immediately escape after one thermal accommodation step happening with the ground. So helium hits the ground, thermally accommodates, and after 1 or 2 hops of this energy, it's almost guaranteed to be lost because it's going to accelerate above escape velocity. It all changes on the night side, though, where once it happens to get to the night side, once it jumps on the night side, where temperatures are way, way lower, going down to 100 Kelvin, on colder places, 70, 50 Kelvin, you get other effects where temperature isn't high enough. The velocity isn't high enough. It cannot escape. It will do shorter and shorter and shorter bounces, accumulate on the night side, not quite getting stuck there because temperature is still too high for helium to really condense on that side, but really to accumulate until the moon is really rotating and rotating enough for all of these particles to then again be on the day side and have the chance to escape again. So this is really a typical view for any kind of particle that is very light, escaping on the day side, accumulating on the night side. For methane on the left, and I didn't write it there, but it's argon on the right, we see a different kind of global dynamic. So for methane and argon, we have the problem or the additional feature that now the interaction with the surface cannot be ignored entirely. There are not that many, if at all, really conversion reactions or anything going on. But what's going to happen is that the lunar surface temperature are now low enough for these particles to actually condense. And this primarily happens on the night side. So what you see is a complete reverse of what we saw for helium, where once particles make it to the night side, they kind of get stuck on the night side. It's too cold, they condense on the night side. They are removed from the exosphere because they stay on the lunar surface. Now, again, the moon turns, and after half a day, the night side, or everything that accumulated on the night side, will be going to the sunrise section, to 6 o'clock local time right here, where you can see this very nice and pronounced peak in the exosphere densities, at the surface densities, because this is where the sudden increase in temperature due to the sunrise will lead to a sudden increase in energy provided to these particles, and everything will be released almost immediately around this 6 o'clock mark. And you can see then it flattens out, it goes lower and lower and lower, not quite getting zero on the entire day side, but once the sun sets, once the temperature is really lower again, it again starts to condensate on the night side. And you see a similar picture for argon. The main problem is just that the author just shifted a little bit the x-axis. So in this instance, I think you have, the sunrise here on the right and the sunset here on the left. So their day side and night side is switched, but it's the exact same kind of dynamic, where here at sunrise, you have a lot of argon immediately or all at once being released due to the sunrise, due to the sudden increase in temperature. Nonetheless, I was quite happy with the results. So I would say, rather simple model worked with a variety of different particles. I was able to get good results that are comparable to other results that you can find in the literature. Which then said, okay, wonderful, that works. My professor told me water is one of the more interesting particles that he wants to look at. And I think back then, one of the last things I did during my internship was actually to let a simulation run for water. But then very quickly, it became apparent that water is a little bit more tricky, hydrogen particles as well, because there's not just an absorption or condensation happening, there's an actual reaction happening when protons, hydrogen, hydroxyl water is hitting the lunar ground, and certain stuff can happen, which I'm going to touch in a minute. Nonetheless, my model worked good enough, so I said, okay, I'm going to spend some time cleaning it up. I spent some time documenting, spent some time really making a code package for myself out of this, because then I could take all of my model efforts that I did for my master thesis, put it into my doctorate, and then keep working on it. And I said, okay, I want to make it right this time and not just write messy code. So I created this access package in the programming language Julia, it's quite new, but I always take a minute to introduce the new language to an audience every time I have a presentation. I think it's now a little over a century old, but it's especially made for scientific computing and has very, very good libraries for the entire differential equation machine learning part of things. Even though machine learning is not that much of a deal, differential equations is coming in very, very handy. And it's just a very good high performance language that is easy to learn and very easy to code in, which is, I would say, at this point, I'm convinced to be a little better than Python, but that's always a very tricky stance to have at least in the numerical community. And in my package, I included now a lot of things, tried to investigate it a little bit more. I'm more quickly going through it right now. I looked at different velocity distributions that can happen on the ground based on thermal release, mostly based on Maxwell-Boltzmann velocities, but some people already investigated it and said, no, in order to have a usual exosphere or a usual atmosphere, and because the surface of the moon is very, very rough, you don't have these nice directions that you would see in the Maxwell-Boltzmann velocity distribution, but you'd rather have a more focused or a flux component in it. So people derived the Maxwell-Boltzmann flux velocity distribution to better match what they can see in exospheres, and yeah, found that this is to really model how particles are released from a rough surface, a better approximation than just using Maxwell-Boltzmann velocity distributions. I went from 2D velocity trajectories to 3D trajectories. Now, again, this is kind of a fake because it's a 2D animation, but I think you get the idea. I'm now not only calculating the landing position, but I implemented fast trajectory solvers so I can really see where do my particles originate, where do they fly. And here, in this instance, it is the moon in the middle, and I implemented, I think it's about 200 trajectories of helium. And I just want to point out that I really like this animation. I put it in almost all of my presentations because you can really see how far spread it just the thermal release of helium can get over the entire moon. You have single particle trajectories that reach over the entire side of the moon, reaching more than 180 degrees around it. Basically, you have the one very big one that goes above, which lands basically on the exact opposite side of the moon. So you can have particles launching somewhere, going on one hop through the exosphere and landing on a completely different place on the moon. So it really shows that, especially these light particles, they are very mobile and can get basically everywhere. Yuri already introduced. Temperature is a very important aspect, and I also wanted to investigate it. So I implemented a couple of different temperature distributions. The top ones, the transient one, as well as I think the center ones, are all based on diviner measurements, either the actual snapshots or the ones centered around the subsolar point, depending on what simulation you're going for. There's a averaged version right there on the center left. And then in the bottom row, you also have from different other papers, some temperature distributions that were analytically derived to be a little bit handier when it comes to simulation approaches. Especially the last one is very nice because you can really see for the moon, what happens is that even though it very quickly responds to sunlight, there's still some kind of thermal inertia happening. You see that especially for the distributions where I included this 100 Kelvin line, that the 100 Kelvin line is quickly exceeded at sunrise at 6 o'clock local time. But on the sunset side of things, you see it's narrowing down towards the equator more and more because the moon still has some thermal inertia, keeping the surface temperature above 100 degrees for an additional quarter of a lunar day. And using very simple temperature distributions like this one from, I think it's Butler et al. In the 1990s or something, where it's really just, okay, on the night side, we have one temperature, on the day side, we have some cosine distribution. You can go for it, but it's not that accurate. At least it's not taking into account the thermal inertia. And then newer attempts, I think the right one is from 2015, also included this thermal inertia tail, which is a lot closer and a lot better to use in simulation attempts to go for. Now, one more thing, I obviously included different kinds of discretization. So I really tried to pack all of the things that I need as a modeler for my global simulations into one package. I just included one of my discretization schemes. There are lots and lots and lots of them out there, and lots of people who did derive them that are very, very smart and have very good ideas. So I just try to use all of this and put all of this in one package to now just have one code base, one function library base that I can use for my simulations. I already covered this. This is basically my advertisement slide for Julia, the programming language. I can just say, check it out. If you want to use or want to learn another programming language, I can just recommend that to everyone. I think it was 13 years ago when the developers at MIT introduced this new language. They had the goal in mind to be as simple as Python, as quick as C. That's the catchphrase that you can see everywhere. And I'd say they got a long way. It's very easy to learn, especially if you have a MATLAB background, because the syntax is very, very simple. And this is a huge thing, especially in the university context, because at least from our side, students usually learn MATLAB. So they know how MATLAB works, they know this syntax. And for Python, sometimes indexing goes wrong, sometimes other things go wrong. But if they switch to Julia, it's usually a lot easier. They get good results. It's very easy to learn. It's very good for teaching. So just a general recommendation if you want to check something out. I even included the link. Yes. Now, what's in my focus right now? Everything that I showed you before was basically my code base, and now I want to implement it. And Julia already introduced, I am now looking at the water cycle, or at the water exosphere simulation. And the main new thing that now comes into play is that for water or for hydrogen-based species, you cannot really take one species and just simulate that one. You cannot say, I'm just looking at hydrogen now, and that's it. And then I'm looking at molecular hydrogen, and then I'm looking at water. You have to have a complete overview over them because they are inherently connected. And they're connected through the exosphere, through photodissociation processes. And you see that it's not negligible, especially for water. You have some photodissociation processes which just happen at a very, very high rate. The dissociation from water to hydroxyl and hydrogen is definitely not negligible. And this creates this very strong bond between whatever water you have in the exosphere and whatever hydroxyl and hydrogen you have in the exosphere. So all of these highlighted reactions are really what's binding or coupling these different species, meaning that you somehow, even though it's a exosphere where, especially because of your assumption of a Monte Carlo simulation, cannot couple these directly, you still have to look at them in one entire simulation where you have to introduce that coupling somehow. And the second way where these species are coupled, not just in the exosphere, also in the surface. And here the tricky part really much begins, because we already know that there is going to be some kind of reaction going on, especially protons coming from the solar wind, implanting in the lunar ground, finding some oxygen dangling around in all of these metal oxides of the ground, and then reacting to OH, to water. But the real question is, how does it happen and how often does it happen? How frequent? What's the rate there? And I really wanted to give you better rates, but this is really the newspaper I can find over 20 years ago, where people tried to investigate this, tried to model this, and found that for their model, for whatever they knew, there has to be some probability, some branching probability for one proton entering one ground, entering one surface interaction, and then exiting as H2, as OH, as H2O. And you see these go lower and lower with only a 2% chance that a proton coming from the solar wind is then going into the ground. And these are very rough values. The authors even comment on this in the paper saying, we don't even know the error bars to it. They're probably massive, but this is what worked for us. And this sparked really much my research saying, okay, we have to do something about it. We have to look at it and now do one simulation where we put it all together. And the main idea was to say, okay, I'm simulating all these 4 different species. I'm counting what are they lost to? Are they lost to dissociation? Are they lost to surface conversion? Are they lost to something else? And every time this loss process included a conversion to a different particle, I stored that and said, okay, next iteration, I'm going through all of my stored particles. And then next iteration, I'm going through all of these stored particles. And then after a couple of iterations, all of these different particles, all of these 4 species are, let's say, sufficiently coupled so that you can actually see a dynamic change based on each different species. And the results look something like this. Now, before I go through what these results actually look like, I just want to quickly go through what you can actually see. I already told you about the x-axis being the local time. And the local time is really just a different representation of the subsolar longitude. So just a very easy way to get a feeling for, okay, that's sunrise, that's sunset, and that's noon. And I just wanted to point it out here. So all of the plots that you're going to see, and I think I haven't seen many people in the modeling community to use subsolar longitudes. They all just go for local time because it's a little bit more handy and you can have a better feeling at what position you're currently looking at. On the y-axis, we only have the upper hemisphere because for this simulation, I said, okay, the moon's inclination towards the sun is about 1.6 degrees. The real difference that you will see between the upper and the lower hemisphere isn't even modeled. There will be complete symmetry. At least I'm going to expect complete symmetry. I'm modeling it so that the equator is not inclined towards the sun. So I can only look at the top hemisphere and say, okay, equatorial symmetry is handling the rest. So at the bottom, you will see the equator, and the further up you go, you have then the polar region. Now, one main thing is don't mind these exact values because these are based mostly on what you see in this paper from 2002 of these branching probabilities, one proton hitting the lunar surface and then being converted to something else. So what I'm trying to say here, or what I try to convey in my paper is, don't look too much at the exact values, look at the dynamics change. Because in what you see here, I more or less completely ignored, completely disabled the conversion process. So I disabled this surface reactivity, saying all of these branching probabilities, they are basically not happening. It's a 0% chance of it happening. Each individual simulation is on its own. And you see very nicely for the top left, you have atomic hydrogen. It's coming mostly from the sun, from the solar wind. So you will have something centered around the subsolar point. You will there see a higher density, but simply because it's so light, it's immediately going to escape. This is why you don't have that much of a signature on the night side. It's 1, maybe 2 hops, and then it's gone because it's so light. Similar for H2, also way too light to stay for a long time in the lunar exosphere. So after 1, 2, 3 hops, it's usually gone. And you see this very nice focus around the subsolar point because that's where basically everything is coming from. Now, for OH and H2O, remember what we saw with the argon and for the methane distributions, you again have this nice peaking behavior around 6 o'clock, around sunrise, because for OH and H2O, you again have species that can condense, that can react on the night side because of the low temperatures, getting stuck on the night side, and then experiencing this sudden release due to the increasing temperatures on sunrise. And without, again, looking at the exact numbers, I just want you to focus on what happens if I now switch on the surface reactivity. And the most significant change you will see for the atomic hydrogen. So 3, 2, 1. That's the main difference I was excited about. So the main difference right now is that you can see that out of the sudden, OH and H2O have a significant influence on the distribution on the surface number density for hydrogen. And even though hydrogen cannot inherently condense on the night side because it's too light, because its activation energy is way, way too low, you still see this very nice desorption peak evolving also for the light species, also for hydrogen, because it's so well coupled now to OH, to H2O. So as soon as you up the coupling between the different species, you will see fractures of these things as well in other signatures. So a dramatic change in the dynamics of the exosphere. Now, it still remains to be seen is how dramatic is it really, right? So as I said, the numbers are really just an estimation, and it can vary by 1-2 orders of magnitude. Maybe this peak will not be as pronounced as you can see it here, but I will be pretty sure that there will be some kind of peak visible due to the coupling. If we look at it just at the equator, I put all of my simulations I did back then in just one graph. For OH and H2O, not much really changes. You have this nice peaking behavior around 6 o'clock, and then it flattens out. On the night side, there's not much going on. Again, the more interesting part is hydrogen, atomic hydrogen, where for the black curve, where you have almost no reactivity, the number at the top says how much reactivity is enabled. 25% is almost nothing in this case. And you see there's not much going on. At 6 o'clock, no real difference. But as soon as you up the reactivity, as soon as you couple these particles more and more and more, you see this very nice peaking behavior going at 6 o'clock. Now you would, if you magnify it and if you would do some statistics, also see it for H2, but it's way less pronounced for H2 than it is for H. Nonetheless, there are many not sightings, many experiments that have already seen that there's some kinds of asymmetry between the morning terminator, the sunrise density for H2 and the sunset density for H2. And they still are trying to figure out why that is. Some say, okay, you still have this, remember this thermal tail on the sunset side where it's not quite flattening out as quick as it rises on the sunrise. Some say, okay, maybe, or I say, maybe it could be that there's this coupling between all these different species, and because OH and H2O is inherently higher at the sunrise, you will also have this asymmetry in the H2 curve where you just have higher values at sunrise. So I used this very simple graph and created a more complex graph, and please don't take the time and look at it. It's just, I tried to find everything that I could in literature, try to find, okay, what different kinds of reactions have I going on between adsorbed species, gaseous species, between particles that are in the regolith, that are in the exosphere, and try to point out everything that we might know or might not yet know. And this is basically the graph, the metro map, we called it, that I came up with. Nothing that is yet implemented, but something that is really just guiding me right now to get a better feeling of what's out there, what have others already found. And most papers that you find are really just looking at then sub-networks of this entire network, trying to simulate it. And this is my main thing, why I'm here, why I'm very excited to be here, and hopefully we'll get a couple of new insights, because as Yuri already said, we want to do some experiments together. For me, I have to be very honest, it's a very big learning experience, because I'm just a numerical scientist. I have done very, very little experimenting in my days, and I just want to compensate for that fact. I really want to stand in the lab and learn a little bit about experimenting, see what problems you can get when you do actual experiments and not just type things into your computer. So he proposed an experiment. We talked about it today. Hopefully next year we can work in it. And the main idea is really to, again, use a subnetwork here, irradiate samples, and look at not the exospheric behavior, that is a little tricky to simulate in the lab, but look at the behavior of proton implantation, of hydrogen implantation into some regolith simulant material here in the lab. And the main idea behind what I want to get out of this is, if you remember this 20-year-old paper that said there's a rough 60% chance that protons entering the lunar regolith will exit as H2. I want to put constraints on that. There are no error bars as of yet, and people said, okay, there must be these and these rates, and this is a first order, this is a second order process. Now I want to get a little bit closer to figuring out what it really is. And I know there won't be an exact perfect answer, but getting a bit better feeling of, is it really a 60% to 10% chance that a particle will get to H2 instead of OH? Or is it a 60 to 5% chance? Or is it depending on the temperature, which it most likely is? So this is really what I'm trying to, or what we will try to figure out. I highlighted TBD measurements, but the real end is just that I'm very excited to hopefully perform these experiments, to learn a lot along the way, and hopefully use whatever we can find in these experiments to improve the framework, and then redo the simulations to really see, is this dramatic global change in the exosphere something we should be seeing if there would be another measurement going on? Improve the framework, improve this coupling process, and then hopefully improve our knowledge about the lunar water exosphere. And that's it. I hope I didn't take too long. Thank you very much, and thank you for your attention.
Are there any questions? Or I can start with one, and then whatever comes to your mind. We have the room reserved until 3 p.m. It's still old time, so for another hour, I hope I'll not keep you here for another hour, but anything that comes to mind. This is really interesting topic, and also in the light of new interest in the moon. That's a lot of nations are planning to go to the moon. Of course, they're planning to build a station orbiting the moon. And of course, there is always the question of in situ, right, utilization of material. And in this light, water is extremely important. First, as something that you astronauts or people who are settled on the moon can drink, and the second as a source of as a rocket fuel. Of course, you can always separate water into oxygen and hydrogen, and then use it as a propulsion agent. So my first question would be, if you go back to these graphs, we know that the lunar day lasts for 29 days, right? So when you put conveniently 0 to 24 hours, does that mean that each hour is then 29.5 hours long?
Yes.
Just to clarify this, that you get the, so this is kind of a slow motion day, right? Yeah, exactly.
So it's just an arbitrary, it's not really 1 hour, as you pointed out. It's just a way to represent it a little
so
bit better.
We can imagine it in our terms. Okay, then the second thing, when you mentioned you were doing your nice advertisement for Julia, is that, does it run like Python does, that you need an interpreter, or is it more like C++ that you, let's say, you have the executable and then you can run it?
It's really much like Python. So
it's like Python.
Once you basically know either MATLAB or Python, or both, ideally, you're in the terms of how to use the syntax, it's almost identical. So it's very, very easy to use.
When you said that it's fast as C++ or C,
it's very fast.
Okay, but do you need to have an engine behind running, or you get an executable out of it once you have like...
You have the engine running, you don't get the executable out.
Okay.
Yeah. So, I mean, I have to say that for these simulations, I actually obviously ran them on a cluster server. And for the first time, I was actually then using hopefully all of my high performance code. But I don't really think that for most of the things that I'm doing, it's really noticeable, especially for the small ones, whether I do it in Python or in Julia, it's almost the same thing. But when you start optimizing things, start benchmarking all of it, and now that I have my code base where I'm doing a lot of benchmarking lately, a lot of testing lately, I'm very much confident that at least pure Python packages would never be this quick. Now, I'm an engineer by trade, so I'm having a mechanical engineering background. I'm trying to go more into the planetary science direction, so I'm not a computer scientist.
Yeah.
So there's probably people who can do it way better than I do, but I made very great experiences with it. So this is just my general recommendation.
Okay. Now, one more question, and then I'll let others ask. But when we were talking, also there is an important role that, and you mentioned it in the talk, that micrometeorites play in all this. So recently, a Chinese expedition brought a bunch of glass beads from the moon to the Earth, and they analyzed it, right, and found a great content of water inside those glass beads. Can something like this be done in the lab as well? And what can we do to simulate the impact of micrometeorites, and how could we kind of approach this?
So the main idea behind why micrometeorite impact is so important, and also a very important aspect to study, is that people already found that the water creation process is just requiring a little too much thermal energy, more than we usually have on the moon. So it usually says that there is no significant amount of water being created if you're below 400 Kelvin. And you remember 400 Kelvin was really much the upper border that you can reach on surface temperatures on the moon. So there's this slight mismatch that people said, okay, we know there's water, or we expect that there's water, but there's essentially not enough energy for water to actually be created. And the solution here is micrometeorite impacts, that you have very small meteoroids hitting that and having a very localized effect, where you can have localized a lot higher temperatures, sparking this reaction, creating water, creating these glass beads, where then the water is trapped inside. And the main idea to reproduce it in the lab is, well, if we could shoot particles on the regolith bed inside of a vacuum chamber and not destroy any of the pumps, that would be great. Otherwise, the idea is any kind of energy delivery system. Easiest would be laser beams, to say, okay, we're pointing a laser at the position where we want to locally increase the temperature. It doesn't have to be by much. So if you're already at plus 100 degrees Celsius, you can have very, very short pulses, bringing it over this 400, 450 Kelvin line. And then depending on what you study, what you want to study, how quickly does it fall off again, how much water is then created inside of a glass bead or inside of the regolith. So it kind of depends on what you want to study, but the main idea is to provide the energy through a different kind of system, through a laser beam, and then trigger this reaction through this laser.
Any other questions?
So, thank you. It's very interesting. By these assumptions, you rule out that some water originates from the craters we see on the moon once. So it means that water that contains these impacts is immediately evaporate 100%, or there are some potential mechanisms that would result in some water trapped.
Yes, so that's actually a very, very interesting point. The main problem is that usually I say once it's in the trap, it never gets out. But the actual lifetime of particles, water particles trapped in these permanently shadowed regions, is actually not limited by will it ever get this hot, but it's limited by what's my micrometeorite flux. So really much, if you have craters with a decent shape that protects you from a lot of micrometeorite impacts, and on the south and north pole you have some that are quite protected, but I'm also not the expert there. The main idea is you can see at how high is my micrometeorite flux, how likely is it that one of these micrometeorites will hit my cold trap, will hit my permanently shadowed region, and then release all the water. But yeah, it's micrometeorite impacts, both evaporating the water that it's hit, bringing water to the lunar surface. And another major point that is gaining popularity in this field very, very quickly is actually man-made water. So now we want to go to the moon, we want to land on the moon, and many people want to do it. And in the next 10, 15, 20 years, more and more people want to do it. So every time we fly to the moon and land on the moon, we have all of our exhaust gases, we have everything, we have a lot of very interesting dust environment as well, because as you saw in my animation, these particles, especially the light ones, can fly everywhere. Even if you land just on the lunar south pole, whatever your exhaust gas is, because it's going to be quite hot, it's going to fly everywhere. And it's going to, quote unquote, pollute the moon. And you will, I don't know, no one really knows at this point, pollute areas where even no one has landed yet. And the next time we measure something there, maybe we see some water that originated from Earth because we brought it to the moon. So that's actually something where people are currently also investigating what happens if we have a very localized, but big source, not just micrometeoroids, but really rockets that are landing, starting on the moon. So there are a lot of interesting things. And then again, it may make a difference whether while we land, we are flying over a crater or we're staying behind a crater. How much of then the exhaust gas is going to go inside of the crater, is then going to be trapped? Do we have to land very far away and then travel to the crater and then measure the crater in order to make sure that none of our particles that we brought with will actually be measured then? So there's a huge problem with the popularity of going to the moon lately, especially in this instance. And yeah, as for now, my research on my model is just looking at solar wind and then micrometeoroids, but man-made things is probably the next step, depending on how long I will keep working that topic.
Thanks. Maybe another bit far away. So in your case, solar wind is actually bringing the matter into the system. So hydrogen in some sort. In Mars, it's a source of depletion from the atmosphere. If you take into consideration your processes, which process directly is there responsible to sweep away the gas from the atmosphere? You showed us some interaction between solar wind. Which process in Mars is directly responsible to sweep away the gas from the atmosphere?
I'm not sure about Mars. So short answer is I cannot answer these things on Mars.
Is it just, I don't know, guessing kinematic collision with gas molecules that get some velocity, escape velocity out, or what could be the reason?
There probably, I mean, because Mars has some substantial atmosphere, there's going to be the atmospheric layer before the exosphere of Mars will also have an exosphere at some point, at some height. And the question really is also something that's not yet implemented and still an open topic, is how much just radiation or solar pressure will change the height profile of the exosphere. And then the moon should be more affected than obviously Mars, simply because of the proximity to the sun. I cannot really answer that directly. The main idea probably for Mars is that as soon as you get thicker and thicker, you kind of have shielding effects. So particles from the solar wind will not hit Mars, but will hit something that's in the atmosphere. And when 400, 500 kilometers per second particles will hit something, there's going to be a probability that these particles will just be removed from the exosphere or from the atmosphere.
Yeah. So, and maybe to go to even higher density system, that's Earth atmosphere, the same trapping like on the poles that you have now for water on the moon is PCBs, this very highly environmentally toxic forever chemicals that after this hopping around also end up at the poles. It process at very different densities, but this hopping happens also on the Earth for certain species. And then you have very high concentrations on both because they act like cold traps. So it's analog, but very far analog to what you showed us. Thanks.
Anybody else? If not, then let's thank our speaker again and we conclude this seminar. Thank you.
Thank you very much.